Right, grade 12s, we're 3 topics down. So we've done first principles, we've done our new rules, we did exponentials and log functions, and now we're on to topic 4. There are 5 topics. There's actually 6, but we can't do the 6th one for now. I'll explain that later. So on to topic 4, called implicit differentiation. Implicit coming from the word implied. Definitely a really cool topic, but a little bit of a tough one. So I'm going to try and explain really slowly, and please, this might need some FaceTime explanation if you are struggling. So let's go a bit slowly. So the introduction that I wrote here says, a function is said to be explicit. If I say to you being very explicit, it means you're being very, I explicitly told you, means I very clearly told you. So in maths, a function is said to be explicit if it can be written in the form y equals. So for example, straight lines we write as y as mx plus c. Parabolas we can isolate y. But what happens when y is not given as the subject of the formula, and either it's not easily possible to isolate y, or it's not at all possible to isolate y? How do we then differentiate if we can't isolate y? So for example, if we had y cubed plus 2y squared minus x squared plus 4x equals 0, how would you possibly isolate y on its own here? Because you couldn't possibly just leave the y's on one side and then factorize out y, because y isn't a highest common factor. So there are lots of complicated ways to make y the subject of the formula, or we can do something called implicit differentiation. So let's do an example, and I'll explain this as we go. So in example 1, it says this exact example I gave in the introduction. How could I possibly differentiate this? Now the whole premise of implicit differentiation is you have to assume that y is equal to something and you don't know what. So you don't know y is some function of x. The point is you haven't been able to figure out what function it is. So you can't differentiate y explicitly because you don't actually know what y equals to. But ultimately, if it was possible to isolate y would be equal to some function of x. So therefore, if you want to differentiate y with respect to x, you can't actually explicitly tell me what this is equal to. So what we do is we simply call the derivative dy dx. I don't actually know what it's equal to, so instead of writing what it's equal to, I'm just going to write the fact that if I did know the derivative, I would put it here. So let me explain to you what I mean. And again, I'm going to go slowly. There are a couple of terms here. There's 4 terms, and when you differentiate each term individually. So let's have a look at y cubed. Now y, I don't know what y is. If I knew what y is equal to, it's basically something cubed. Now I don't know what y is equal to, so I've left that blank. Now how would you differentiate something cubed? If there's a function inside here, I'm hoping that you would agree with me that this would be the chain rule. And to differentiate the chain rule, you would differentiate the outside function. So I would bring down the 3, I would leave the function inside, I would minus 1, and then I would multiply by the derivative of the inside. So derivative of the inside function, so the derivative of that. Now the problem is I don't know what that is. I don't know what y is equal to in terms of x because I can't get it. So what we do is we just leave it as y. So we bring down the 3, we say it's 3. Now I don't know what y is, so I'm going to leave it as y squared multiplied by the derivative of inside, which is the derivative of y. And so I'm just going to write that as the derivative of y with respect to x, because I can't explicitly write it at the moment. If I could, I would write it there. So what that is that entire thing is the derivative of that first function, viewing it as a chain rule and y as a function, and I don't know what y is, so I just keep the symbols. So I keep y as the inside function, and the derivative of y I just write as dy dx since I don't know what it is. Now if I look at this next one, that next term is also a chain rule. Remember, 2 is not a function of x, so I wouldn't see this as a product. That's just a coefficient. This again is a chain rule. So I'm seeing this as plus 2 and it's something squared. So I'm going to bring down the 2, so I get plus 4. I'm going to leave the inside function alone and say to the power of 1. Now, what is that inside function? Well, it is some function of x. I just can't write it right now, so we just keep it as y. Now, I multiply by the derivative of this inside function, which is y, and I don't know what y is, so I can't differentiate it explicitly. So I just say, well, I would differentiate y here with respect to x if I could. So that again is very similar to the first term. It's a chain rule. Now this derivative is really easy because that is minus 2x, and this derivative is really easy. That's 4, and this, I've run out of space here, but the whole point of this is, in an equation, the premise that we've always worked on is you can do anything to an equation as long as you do the same thing to both sides. So I have now differentiated the left-hand side. I must differentiate the right-hand side. And the right-hand side, the derivative of 0 is 0. So this is a little bit messy. Let me neaten this up quickly. So this is 3y squared times the derivative of y with respect to x, if I knew what that derivative was, plus 4y times the derivative of y, if I knew what it was, minus 2x plus 4 equals 0. So basically, I have differentiated each term, and it's called implicit differentiation because I haven't explicitly differentiated y because I don't know what y is. So instead of explicitly doing it, I have implicitly done it in that I've just said dy dx. Now, what was the whole point of this? The whole point of this was to find dy dx by itself. So this is almost like isolating dy dx in a literal equation. So what I would do now is I would get rid of all my non-dy dx terms to the other side of this equation. So dy dx. And so I'm going to take the 2x across and the plus 4 across. Then I would literally factorize out dy dx. So I get 3y squared plus 4y, and then I can isolate dy dx. Now this is going to look really weird to us because we've never seen a derivative that has y's in it. You know, derivatives only have x's in them, but that's because y, we've never been different. We've always been able to isolate y. And so this is quite interesting in that the derivative depends on x and on y. It's a mixture of the two. So if you don't know x and y, you can't find this derivative. But that's pretty nifty. Now, implicit differentiation takes a lot of time to master. So I'm going to go over the next one just as slowly. So hopefully, slowly but surely, we'll get used to this idea. So let's look at the next one. Find the derivative of. Well, let's look at term 1. Term 1 is a product. And the first function is x. So x is function number 1, and then y squared is function number 2, and that would be a chain rule because y is some function of x. I just don't know what function it is. So we have to do a product rule. So what did the product rule say? It says differentiate the first function. So the derivative of x is 1, multiply by, leave the second function alone. So multiply by, leave the y squared. Then plus, leave the first function, which is x, multiply by the derivative of the second function. Now, y squared is a chain rule because y is a function of x. I just don't know what. So I need to bring down the 2, leave the inside function alone, minus 1, and I need to multiply by the derivative of that inside function, which is y, because y is a function of x. I just haven't explicitly written it. And what is the derivative of y? Well, I don't know, so I just write the derivative of y with respect to x because I don't explicitly know what it is. So that entire thing is a product rule, and within that product rule, that second function was a chain rule. Right, on to the next term. This is my second term, which is y squared. Now we actually have just differentiated y squared. This bit here, that is the derivative of y squared. So let's just talk through it again. Bring down the exponent of 2, leave the inside function alone to the power of 1. Now notice, if that was x squared, the derivative of x squared is 2x. We don't go times the inside function's derivative. The reason being, this is not an inside function. X is just x. It's only y that is a function of x. We just don't know what that function is. So don't make the mistake of thinking that x squared also is a chain rule. This is only a chain rule because y is a function of x. So it is in itself an inside function. So that's why I will differentiate the inside function, but I'm not explicitly, because I don't know what it is. Okay, then my next term, so that's just minus 2. Again, x isn't an inside function. And then the derivative of 8 is 0. Great. And so what I'm going to do now is neaten this up, collect up my dy dx's. And so this is actually y squared plus 2xy. Sorry, that's not a dash, that was a power of 1 times dy dx. And again, that's a power of 1. I was just being explicit. Times dy dx minus 2 equals 0. So I'm going to do 2 steps in 1 now. So I'm going to factorize out dy dx. So I get 2xy plus 2y equals, and I'm going to take my y squared and my 2 over. And so now I can divide by my coefficient of dy dx, and I'm actually going to write it like that at the top, only because, I don't know, it's just habit not to put a negative in the leading coefficient. 2xy plus 2y. So I hope that made sense there, but basically I took these two terms, I was just cutting corners, I took those two terms and factorized that out, and took the other terms to the other side and isolated dy dx. Again, you'll notice dy dx depends on x and y. If it doesn't depend on x and y, then we probably could have done normal differentiation, because we would have been able to isolate y then from the beginning. So it's always some type of mixture. Okay, let's do another question. Determine the derivative of x squared plus y squared equals 100 at the point. So they've actually given us a point where they want this gradient. Now, just out of interest, x squared plus y squared equals 100 is a circle of radius 10. We haven't done circles yet. We will be doing them. So that's what it looks like. And they're saying that negative 6, 8 will be kind of like a point there. And so they're asking me for whatever the gradient of that tangent at that point. So let's differentiate this. These are two terms. The derivative of x squared is 2x. Again, there's no inside function because x is not a function of anything. It's just x. Whereas this looks identical, but it's a chain rule, because I bring down my exponent, multiply by the inside, but that y inside is a function of x, and so the derivative of the inside is dy dx, and the derivative of 100 is 0. So dy dx, 2y dy dx equals negative 2x. So then if I divide by 2y, the 2's will actually cancel, and it's equal to negative x over y. So now that I know the point, so therefore at negative 6, 8, dy dx will be equal to negative 8 x, I am right. It's negative 6 over 8, which is 6 over 8, which is 3 over 4. Which, due to the fact that I had drawn a picture, I was expecting a positive gradient. And that's pretty cool. That was a pretty nice one. So now we know the derivative at that point, which should be the gradient at that point. Okay, on to example 3. Determine the equation of the tangent. So this, we've done one of these examples before. We've done lots in maths, and then we did one in one of the previous lessons. So it says determine the equation of the tangent to this at that point. Now, what do we know about tangents again? The gradient of the graph at that point equals the gradient of the tangent. So the gradient of the tangent equals the gradient of the graph. Gradient of the graph at, and this point is negative 2, 1. We also know that this point will be a point on both the tangent and the graph, because it's the point where they touch. And so those are the two things that you always know about tangents. So you always have a point on the tangent by default, and you have the gradient if you can find it. Okay, so let's go find this gradient. There are 4 terms here to differentiate, so let's look at this. Right, this is a product rule. You have x and then you have y cubed, so this is going to be function number 1, and this is going to be function number 2, so that's a product rule. Right, the derivative of the first function is the derivative of x, which is 1, multiplied by, leave the second function alone, so y cubed, and then plus, leave the first function alone, multiplied by the derivative of the second function. Now the second function is a chain rule, because y is some function of x, I just don't know what yet. So I bring down the 3, leave the inside function alone, subtract 1, multiply by, differentiate the inside function, which I have to write as dy dx because I don't actually know what y is. On to the next term, 3x squared. That's not a chain rule, it's just 6x, because x isn't a function of anything else. Right, now we have another product, because xy, x would be the first function, and y would be the second function. So product rule, here we go. First I equals, differentiate the first function, which is 1, leave the second function alone, which is y, then plus, leave the first function alone, and then differentiate the second function, which is just the derivative of y. And it's not a chain rule, it's just the derivative of y, which I don't actually know, so I'm going to say dy dx. And then it says plus 12, so the derivative of 12 is 0. That's that one over there. Great, so now we have fairly messy, but let's neaten it up a bit. I'll keep this one. So this is y cubed plus 3xy squared times dy dx plus 6x equals y plus x times dy dx. So remember, this is AP Math, so where you can cut steps because we run out of time fairly often. So I'm going to factorize out my dy dx and bringing everything over at the same time. So that would be 3xy squared. Now if I brought this over here and then factorize out the dy dx, it would be minus x. And then if I kick everything else to the other side, it would be y minus y cubed minus 6x. So you just have to be a little bit careful when you cut corners. But I think that's right, because there's my dy dx term, there's my dy dx term, and I've brought that over, so it's minus x, and then I kicked everything else to the other side. And so finally, I can isolate dy dx by dividing, so it's y minus y cubed minus 6x over 3xy squared minus x. Now that wasn't the full question, that was part of the question. The question says, can you find the gradient at can you find the equation of the tangent at negative 2, 1? So now I need to say, okay, great, I know the gradient at negative 2, 1, because I can use this formula. I think it was negative 2, 1, yes it was. So therefore dy dx would be equal to 1 minus 1 cubed minus 6 times negative 2 all over 3 times negative 2 times 1 squared minus negative 2. Now I'd probably just use my calculator to work this out. And I think I get negative 3 if I did that correctly, which is great, because now I know that my tangent is y is equal to negative 3x plus c. And I've been given a point, which is really nice. So I can substitute in that point. I can say when y is 1, x is negative 2, and that'll be 6. So if I subtract 6 on both sides, so I run out of space here, I get y is equal to negative 3x minus 5. So actually, once you've found the formula for the derivative, from then it flows really easy. You sub in, you find gradient, and you can sub in a point. So that was quite cool. Okay, on to the next one. Given 3x squared minus xy plus 4y squared equals 141, determine the values of x where the tangent to the curve is parallel to the x-axis. So what does that mean? I don't know, there's some funny curve here, I don't know what it is, and they want to know where the tangent is parallel to the x-axis. So if you're parallel to the x-axis, what's your gradient? Now I'm hoping you know that therefore your gradient is 0. So basically parallel to the x-axis means my gradient is nothing. So hopefully I can just differentiate and find out where my gradient is equal to 0. So let's try. First thing, first term, derivative of 3x squared, that's easy, that's just 6x. Okay, minus the derivative of a product. So let's just quickly go write this. Now the first thing I need to remember is I've got to put a bracket. I am subtracting the derivative of that whole product. So if I don't put that bracket in, it goes horribly wrong. So first function is x, second function is y, and the rule says that you differentiate the first function, which is 1, leave the second function, which is y, and then plus leave the first function, differentiate the second, which I would write as dy dx. But notice that bracket is absolutely essential because I'm subtracting the whole of that derivative. Now I've got plus 4y squared, which is a chain rule because it's plus, bring down the 2, so 8y, but multiply by the derivative of the inside function, which is y, which I don't know, and that equals 0 because the derivative of 141 is 0. So to neaten up, I get 6x minus y minus x dy dx plus 8y times dy dx equals 0. So factorize out dy dx and I'll get negative x plus 8y. Take everything else over and I'll get y minus 6x. And so dy dx is better written as y minus 6x over 8y minus x. Just swap that around to make it look prettier. And that's wonderful. The question was, when is it parallel to the x-axis, which would mean my derivative is 0. So 0 equals y minus 6x over 8y minus x, which means that if I multiply by this denominator on both sides, multiply by 8y minus x on both sides, it'll cancel. And actually, I'll get the fact that 0 must be equal to y minus 6x. So y must equal 6x. Now, that hasn't answered the question, because this question says determine the values of x where the tangent is parallel to the x-axis. So I know that y has to equal 6x for this to be happening, but I haven't actually solved for a value of x. So this is quite a difficult question, because what we need to realize now is, on the one hand, y has to equal 6x has to be true for this to happen. On the other hand, this equation of the original function has to still be satisfied. And so this now becomes a simultaneous equation, because on the one hand y has to equal 6x for this to happen, and on the other hand this top relationship between y and x still has to hold. And so I really didn't expect to run out of so much space, so let me maybe draw a line down here. And so what I need to do is now do a simultaneous equation and plunk that into there. So now I'm going to get 3x squared minus xy plus 4y squared equals 141. Sorry, I really haven't done well on my spacing here. So now I get 3x squared minus 6x squared plus 24. Oh no, sorry, not 24, because I have to square the 6 as well. So it actually becomes 4 times, and this is going to be 36x squared, and so that is plus 144, I think, x squared, I better check that on my calculator, equals 141. So let me just quickly check that. Right, so I think I got that right. So 3x squared minus 6x squared is minus 3x squared plus 144x squared actually becomes 141x squared. And so I actually then get the fact that x squared must be 1, which means x is plus or minus 1. Because remember, when you root, that's technically a quadratic equation, and I could solve it differently. But in AP Maths, I would just rather root and remember the plus or minus. Now, that is really not a nice question. Quite mean, because I think most people would have got stuck at, that's wonderful, y equals 6x, but now how do I find what x is? Don't forget that any equation involving x and y is an equation that has to remain true for all points. So what happens is you found out information about these points. You found out the fact that y equals 6x has to be true at these points. But the original equation also has to always be true at every point. And so that's what made it a simultaneous. Really interesting question. Okay, so I think this is our second last one. Example 5 says determine the equation of the normal to the curve 2x cubed y plus 2y to the power 4 equals 2 plus x4 at 2, 1. Now, as science students, I'm hoping that we know what a normal is. A normal is a perpendicular line. That's just a fancy word for a perpendicular line. And so what do we know about lines that are perpendicular? We know that their gradients have a relationship. The gradients will multiply together to give you minus 1. So if you know the gradient of the curve at this point, that'll be the same as the gradient of the tangent, and the perpendicular line will have some relationship, and we'll look at that. So let us implicitly differentiate this. Right, what omission? That is a product rule. So 2x cubed, y is a product rule. Let's think of this as function number 1. Let's think of this as function number 2. And the product rule says differentiate the first function. So that would be 6x squared. Leave the second function alone. Plus, leave the first function, so 2x cubed. Multiply by differentiate the second function, which I don't actually know what it is. So I'm just going to write dy dx. On to the next one. This second term is a chain rule, because I'm going to bring down the 4, so it's 8y cubed, but multiply by the derivative of my inside function. And then the derivative of 2 is nothing, and the derivative of x to the power of 4 is 4x cubed. So if I isolate dy dx, and sometimes I start to get really lazy and do multiple steps in once, which is absolutely fine in AP Maths. So I'm going to factorize out my dy dx. I'm going to take everything else to the right hand side, x squared y, and I finally have isolated dy dx because it's 4x squared minus 6x squared y divided by that bracket. Now, what was the question here? The question said determine the equation of the normal. So I need to first find the gradient at 2, 1, because they've given me that point. So therefore, at 2, 1, dy dx would be equal to 4 times 2 squared minus 6 times 2 squared times 1 all over 2 times 2 cubed plus 8 times 1 cubed. So absolutely use your calculator. And I got minus 1/3. So that's the equation of the graph at this point, which means the tangent would be the same as this point. But that means the gradient of the normal, and don't forget we just used the trick. The gradient of the normal is, if lines are perpendicular, you swap the gradient around and you change the sign. So if I swap it around, I get 3 over 1, which is 3, and I change the sign. Why? Because let's just think about it. What would you have to multiply negative 1/3 by to get negative 1? And it's 3. So they asked me for my gradient of my normal. They could have actually asked me for the equation of my normal. Oh, wait, they did. So I need to continue then. I know the point. The point is 2, 1. So I now know that this graph is y is equal to 3x plus c. So if I substitute in 2, 1, I get c is minus 5. And so y is equal to 3x minus 5. Great. Okay, so that was the idea of a normal. Right, so my last example seems to go on forever. Find the equations of the tangents to 4x squared plus y squared equals 72 that are perpendicular that are perpendicular to the line 2y plus x plus 3. So this idea of perpendicular again. So first of all, I need to isolate y here, just so that I can see what this graph's gradient is. So this line's gradient is minus a half. So if that gradient is minus a half, what would the gradient of the perpendicular line be? So that's a perpendicular symbol. That gradient would be 2. So they're actually saying find the equations of the tangents to 4x squared plus y squared is 72 that have a gradient of 2. So the tangents must have a gradient of 2, which means the graph has to have a gradient of 2. So where will this graph have a gradient of 2? Well, let's go and differentiate. This is 8x as a derivative. This second term is a chain rule, so it's 2y times dy dx, and the derivative of 72 is 0. So if I isolate dy dx is equal to negative 8x over 2y, so dy dx is equal to negative 4x over y. Now you want this gradient to equal 2. So that's great. So 2 equals negative 4x over y. So if I multiply by y on both sides and divide by 2, I get negative 2x. Now this is exactly the same idea as we got here. We landed up with the fact that we now had a relationship between x and y that has to be true at this point, but it didn't help me find the point. So the same idea happens here. I know that y is equal to negative 2x has to occur at this point, but I need to know something else in order to find this x value, and I do. I know that at this point the coordinates have to also obey, so and 4x squared plus by y squared equals 72 has to also be obeyed at this point. So these x values that I'm trying to find have to obey this first equation and the second equation, which basically means a simultaneous equation. So if I solve this simultaneously, hopefully this isn't so weird the second time round. So this is 4x squared plus y squared has to equal 72. So 4x squared plus what will be 4x squared, so it becomes 8x squared is 72. So x squared is 9. And again, I would just square root both sides and get plus or minus 3. So you notice the simultaneous part of this lands up being really easy because the rest of it is so difficult. Great, so hopefully a couple of things have happened here. Hopefully we've started to become more and more comfortable with implicit differentiation through all of these examples. Hopefully we've revised tangents, we've learned about normals and perpendiculars, and this whole idea of how simultaneous equations can come into it. It's pretty cool. Right, so after that marathon, I've made quite an extensive exercise 3 on implicit differentiation, because it really does come up in every exam, and it can be a little bit tricky at times. So I will save exercise 3 as a PDF. I'll also put the memo, so hopefully you can mark from that. And please, especially in this particular topic, ask questions whenever you want. Okay, well done.